This video is on seasonal decomposition forecasting, Chapter 13 in your text. We will be working an example from your text. Table 13.6 on page 324 contains the data that we will be using. A skincare company has sales data up through the first quarter of 2015. Our task is to forecast future sales for quarters 2, 3, and 4 of 2015. We will be using a multiplicative seasonal model in this example. In the multiplicative model, Y, the actual sales value, is equal to a trend component times a seasonal component times a cyclic effect times random error. Our process will isolate the seasonal factor S. To do that, we rearrange terms in this formula. In this model, seasonality is any cyclic behavior based on the calendar or time of day. The cyclic effect is typically longer term in nature. It is based on the business cycle, the life cycle of the company, or economic cycles, things like that. For our purposes, and in this text, the cyclic factor is considered to be negligible, and we will combine it with random error. So let's isolate the seasonal factor by rearranging terms in this multiplicative equation. Divide both sides of the equation by the trend, T. You'll see that gives us the actual sales divided by trend is equal to the seasonal effect times the combined effect of cyclic behavior and random error. Instead of using the term adjusted seasonal average as in your text, we will be using the term seasonal index. Seasonal index is much more commonly used here in the United States. Let's start with the data set that's on page 328 of your text. Here we have sun cream sales for 13 quarters, and we're asked to forecast quarters 2, 3, and 4 of 2015. We're going to start with the data set including the centered moving average trend. Your textbook does a great job explaining how to create a centered trend. So we're going to start from that point. Our first step is to look at the data. Highlight the Y values that are going to be contained in the plot. Insert a line chart. And you have your plot. We also see that the x-axis, the horizontal axis, is labeled in just period numbers. If you want to make your chart look a little better and include the year and quarter values here, right-click, select Data, edit the horizontal values, selecting all of the years and quarters, click OK, OK, and there we have our data with a more intuitive axis identifier. Our next step is to calculate the seasonal factor percent. This seasonal factor, as in the equation that we showed a couple slides ago, is equal to our actual sales value divided by the trend times 100%. So we'll calculate those values. That's equal to 100 times the value in column D divided by the value in column E. These seasonal factor percentages are raw values for each period in our data set. We need to translate them into average factors per period. For example, the third quarter of 2012, our value is 133.3. The third quarter of the next year is 127, and the third quarter of the year following that is 141. Well, what is the average seasonal factor for the third quarter each year? To do this, let's construct a small table. Our table will consist of the years as the rows, and the columns will be the periods, which in this case are quarters. Could be months or weeks or days. And let's copy the values from column F into this small table. So our first value, 133.3, is third quarter of 2012. Our fourth quarter value is 81.53, and so on. Once we've transferred the values from column F into our small table here, it's easy to calculate the average for each quarter. So we can do that. Now we have an average seasonal factor for each quarter, but these average values also contain much error. If we had no seasonal effects, no cyclic behavior, and no error, then all of the actual observations would fall exactly on the trend line. Since in our calculation of seasonal factors we multiplied by 100% to get those values, if all of our factors fell exactly on the trend line, then they would sum to exactly a value of 100 plus 100 plus 100 plus 100, or 400. If we have quarterly data, these seasonal average factors should sum to 400. If we have monthly data, they should sum to 1200. Weekly data, they would sum to 700. So let's see what the sum is. We get a value close to 400, 396.90, but in our next step, we need to adjust this value so that its sum is actually 400 to keep us from propagating errors as we extend this trend out into the future. So our next step is to calculate a correction factor. That correction factor is equal to 400, which is 4 periods times 100, divided by this sum of 396.9. Our correction factor means that we need to inflate each of these values by 1.00782. So let's calculate the adjusted factor by multiplying this correction factor times each of these quarterly values. If we've corrected the values correctly, then they will sum to exactly the value of 400. And we see that they do. Now these adjusted seasonal values here are what we term as the seasonal index. Let's copy each of these values into our seasonal index in column G. Our first quarter is 2012, quarter 1. So our quarter 1 seasonal index is 71.83. Our second quarterly value is 107.52. And these quarterly values repeat. These are our adjusted seasonal factors. Our next step, this is for convenience in Excel because we're going to do a regression step here following this. We need a usable X value for our regression analysis, and that is the period number. So just number the periods consecutively. Extend that down by selecting all cells and just drag the box down. Now we have all the periods identified. So the next step is to extend the trend from the centered moving average trend that we have here into a straight line regression trend line. This is our predicted trend. To do that, right-click anywhere on the trend line in the graph and select Add Trend Line. It will be a linear trend, and we want to display the equation on the chart. We can see that our regression line is 1.55 times x. Our x is the period value in column H, plus 3.38. Let's calculate this trend line equation so we can get the actual values for each quarter. So that's equal to 1.5505. We see I've transcribed the regression equation into cell I4, and we can just copy that cell throughout the data set. There's our trend line on the plot and our predicted trend values for each quarter in our time series. Our next process then is to generate the forecast values. Our forecast is equal to the predicted trend adjusted for each of the seasonal values. Our average seasonal effect is the seasonal index. So the predicted trend times the seasonal index will give us our forecast values for every period in our series. Since we multiplied by 100 to obtain our seasonal factors early in the process, now we have to divide by 100 to get rid of that effect from our time series. So our forecast values are going to equal our trend, which is in I4, times our seasonal index, which is in G4, divided by 100. So our forecast value of sales in quarter 1 of 2012 is $3.55 thousand compared to our actual value of 6.0. And we can extend our forecast through the series. There are our forecast values. Our last step then is to plot our forecast on our graph, and that will give us an idea of how good our forecast is. Let's select the data. Let's add a series name called forecast. And we'll select the values, click on series values, and pick just the values, not the headers, in this data set. And there you see a final plot of our forecast. The forecast looks pretty good. It's consistent with the time series data. We forecast for future periods sales of $26,980 for second quarter 2015, $35,980 for third quarter, and $24,130 for quarter 4. That is seasonal decomposition forecast using a multiplicative model in Excel. Thanks.